Good morning, class. We are looking at chapter 6, periodic / trigonometric functions. Here's 6.3, part 2, inverse trigonometric functions. Inverse trigonometric functions, part 2. So we've looked at various graphs for sine, cosine, tangent, cotangent, secant, cosecant. We looked at the graphs with phase shift. We looked at inverse sine, cosine, and tangent function, and now more of them. The objectives are to find the exact value of expressions involving the inverse sine, cosine, and tangent function. Define the inverse secant, cosecant, and cotangent functions. Use a calculator to evaluate those. Write a trigonometric expression as an algebraic expression. Again, properties that you have seen many times before. X squared plus y squared equals 1. P has coordinates x comma y. X represents cosine, y represents y. In general, x squared plus y squared equals r squared. Then sine is y over r and cosine is x over r. Fundamental identities include Pythagorean identities, quotient identities, reciprocal identities. Pythagorean identities such as sine squared plus cosine squared equals 1. Quotient such as tangent is sine over cosine, and reciprocal such as cosecant is 1 over sine. Even and odd properties. Even means f of minus x equals f of x. Odd means f of minus x equals minus f of x. All trigonometric functions are odd except cosine, and therefore secant. A periodic function repeats its value at regular intervals. Trigonometric functions are all periodic. K represents an integer. All of them have the period 2 pi except tangent, and therefore cotangent, the period is pi. They repeat after pi or multiples of them. So we looked at inverse sine, cosine, and tangent function, and we said none of the trigonometric functions is one-to-one. None of them has an inverse unless we strict the domain. So in the case of a sine, we strict the domain from minus power 2 to power 2. And of course, the way you restrict it, you want to keep the range intact. The range is from -1 to 1. And you wanted a nice, continuous, smooth curve. So from negative power 2 to power 2, we get that. And we got the inverse. So y equals sine inverse means x equals sine y. And now the domain for the sine inverse between -1 and 1 and ranging between negative power 2 and power 2. Remember, when two functions are inverse functions, domain of one becomes range of the other. So they look like that. And for example, pi over 2 comma 1 for the sine becomes 1 comma pi over 2 for sine inverse. And of course, their composite function is x. What is important to understand, if we say sine inverse sine x, this x must belong to the domain of sine between these two, the restriction, minus power 2 to power 2. If it's sine of sine inverse, it's x, then x belongs to sine inverse, and it must be between -1. We do the same thing with cosine, and to get a smooth, continuous curve, instead of negative power 2 to power 2, we have to go from 0 to pi. And of course, the range is intact from -1 to 1. It becomes a 1-to-1 function. And you graph it, and as an example, 0, 1 becomes 1, 0. Pi -1 becomes -1 pi as far as the graph of its inverse. Therefore, y equals cosine inverse of x means x equals cosine y. Its domain is from -1 to 1, and its range is from 0 to pi. And we write their composite function is x. In the case of cosine inverse cosine x, this x belongs to cosine and it must be between 0 and pi. In case of cosine inverse, this x belongs to the domain of cosine inverse, must be between -1 and 1 to 1. In the case of a tangent, again, not a one-to-one function. The restriction is similar to the restriction for the sine, except the sine, the endpoints are included. Tangent is not, because we have vertical asymptotes. And with this restriction becomes a one-to-one function. And of course, the ranges are real numbers and the graph looks like that. This has two vertical asymptotes. This has two horizontal asymptotes. X equals pi over 2, x equals minus pi over 2 becomes y equals pi over 2, y equals minus pi over 2 for asymptotes. Therefore, y equals tan inverse of x means x equals tan y. Domain for the tan inverses are real numbers, range from negative pi over 2 to pi over 2. And when we write their composite function, in this case, x belongs to tan, must be between negative pi over 2 and pi over 2. In this case, belongs to tan inverse, and all real numbers are okay. So that's what we have covered. And now let's look at this example, and here's the synopsis of what we have covered. The inverse trigonometric functions continued. Find the exact value of an expression involving inverse sine, cosine, and tangent function. So sine of tan inverse of 1/2. Please understand this is an arc or an angle, so you let theta represent that. And that means we are looking for sine theta, everybody. We are looking for sine theta. That's the idea. Because we are dealing with tan inverse, of course, the restriction is similar to sine. It's between negative pi over 2 and pi over 2. That's the restriction for tangent. So tan of theta equals 1/2 by definition of an inverse. X equals tan y, that's what we get. And theta is between negative pi over 2 and pi over 2. Because it's positive, it happens in the first quadrant. And again, tangent and sine have the same sign when it comes to the inverse, because they both happen in the fourth and first quadrant. Fourth and first quadrant. That was the restriction. Therefore, tan of theta is between 0 and pi over 2 because it's positive, so is sine theta. Okay, so theta must be in the first quadrant. So if tangent is 1/2, we can go with two methods. Remember, tan theta is y over x. So that means y is 1, x is 2. And sine theta is y over r. We have to figure out the r. It's x squared plus y squared equals r squared. X squared plus y squared. That means 2 squared, right? Plus 1 squared is 5. And so r is square root of 5. So sine theta is y over r, and it makes it 1 over square root of 5. And by now you know how to rationalize. I quickly remind you again. So just multiply by square root of 5 over square root of 5, and you get square root of 5 over 5. The second method is identities. One of Pythagorean identities is tan squared plus 1 equals secant squared. And so what is tan? 1/2. So put it in here. You get 1/2 squared, which is 1/4. So put it here, squared, you get 1/4. So therefore, secant squared becomes 5 over 4. And secant becomes the square root of that. Square root of 5 halves. Secant is 1 over cosine, and cosine is the reciprocal of that. 2 over square root of 5. Again, we are using identities. We know tangent is sine over cosine. If tangent is sine over cosine, then sine is the product of cosine and sine, cosine and tangent. So sine theta is tan theta, which is 1/2, times cosine theta, which is 2 over square root of 5, and 1 over square root of 5, or square root of 5 over 5, as we have seen it before. In essence, this reminds us of what really happened in the previous section. We are going to move on. Now we want cosine of sine inverse of negative 1/3. Bear in mind, all of them, when they are positive, are in the first quadrant. But when it becomes negative, it depends on the restriction. So just to remind you that sine inverse, okay, happens in the fourth and first quadrant from negative power to power 2, whereas cosine happens between 0 and pi, just to let you know, in the first and the second quadrant. In any event, so we let theta be sine inverse of negative 1/3. That means we are interested in cosine of theta. So sine inverse, this represents an angular arc. So we are looking for cosine theta. That's the concept. And since sine is negative 1/3, and it happens in the fourth quadrant because it's negative. Remember, the restriction for the sine is you go from negative power to power 2 for the sine, so it has an inverse. Okay, so theta is between negative and positive power 2, and also we know that it's equal to y over r. So r is 3 and y is 1. It's important to understand that we are dealing with the fourth quadrant. In fourth quadrant, sine is negative, cosine is positive. Sine is negative 1 over 3, y over r, y becomes negative 1, r becomes 3. X squared plus y squared equals r squared. Y is negative 1 squared, you get 1. R is 3 squared, you get 9. X squared becomes 8. X is square root of 8, or 2 square root of 2. Okay, square root of 8 or 2 square root of 2. And by the way, we are looking at the fourth quadrant. In the fourth quadrant, as well as the first quadrant, x is positive. So we are looking at this situation, everybody. X positive 2 square root of 2, because square root of 8 is 2 square root of 8, as you know that 8 is 4 times 2. 4 comes out as 2. So that's why 2 square root of 2. In any event, So cosine is x over r. 2 square root of 2 over 3, and you're done. That's all there is to it. We can do the second method, sine squared plus cosine squared equals 1 using identities. Now sine squared, you square this number, you get 1 over 9. And of course, this means cosine squared is 1 minus 1 over 9, 8 over 9. So cosine is the square root of 8 over 9. And we know it's positive. We've already established that cosine is positive because of the quadrant. We already know that. So there are two answers, positive and negative. We keep the positive. Now, when you take a root, the bottom becomes 3. The numerator is square root of 8. We established is 2 square root of 2. So that's one way to do that. Very straightforward, everybody. Find the exact value of an expression involving inverse sine, cosine, and tangent function. Tan of cosine inverse of a negative 1/3. So this is an angle. Let theta represent that. So you're looking for tan of theta. In other words, cosine is negative 1/3. That's the idea. Cosine of theta is negative 1/3. Find tangent. And cosine happens, of course, in the first and second quadrant. Remember the restriction for the inverse cosine. And for it to work, we put the cosine, the domain of cosine from 0 to pi. Just remember that. We went from 0 to pi for cosine. So now, if cosine is negative and we go from 0 to pi, it has to happen in quadrant 2. Because in quadrant 1, of course, all of them are positive. In quadrant 2, cosine is negative, so is tangent. So we established the sign. That's extremely important. And we know cosine is x over r. So r must be 3, x must be negative. X squared plus y squared is r squared and makes y 2 square root of 2. By now we should know that. Let me show you this graph. X squared plus y squared equals 9. So we did work it out. Let's just work it out here. X squared is 1, right? Negative 1 quantity squared. Plus y squared equals 9. Y squared is 8. Y is plus minus square root of 8. And we make a decision. We go with positive or negative, okay? In the second quadrant, of course, y is positive. And square root of 8, we have already established is 2 square root of 2. So that should be clear. So we are looking at this piece. We make it larger to make it clear. So this distance is 1. Distance is 1. This is negative 1. This distance is 2 square root of 2. And tangent is y over x, everybody. Y, 2 square root of 2 over x. 2 square root of 2 divided by negative 1 becomes negative. So y over x. That's all. So it's pretty straightforward. We're going to move on. Okay. Inverse secant function. So as you recall, we graph cosine. This is a complete cycle, and then we continue indefinitely. We flip it over, and it becomes secant or 1 over cosine. So we know that. Just like any other trigonometric function, secant is periodic. It fails the horizontal line test. It's not a one-to-one function. So here's what's happening with secant. Y equals secant x. Domain is all real numbers, except x can't be odd multiples of pi over 2 because cosine becomes 0, and those give rise to vertical asymptotes. Range, all real numbers except numbers between -1 and 1, and that's how we write it, which means, let me write in this format. This means, everybody, minus infinity to -1 union 1 to infinity. That's the meaning of it, okay? That means all real numbers except anything between -1 and 1. But -1 and 1 themselves are included. Not a one-to-one function, doesn't have an inverse. So we do the restriction. We do the restriction, and the restriction, since secant is 1 over cosine, we do it just like cosine from 0 to pi. So from 0 to pi. So this was the cosine, everybody. This will be the secant we are going to use. So we're going to use this part and this part. So this part and this part. So with this restriction, we are going to say domain is from 0 to pi, and x can't be pi over 2 because there's only this one. There are infinitely many. This one, there's only one of them here. And it's the same range. We are not going to lose anything because we shouldn't. If we do, that's not acceptable. And this is a one-to-one function, everybody. We were looking for a one-to-one function. So now we write the inverse. Y equals secant inverse of x. By definition means x equals secant y. Range becomes the domain. Domain becomes the range. Okay. So domain, all real numbers except between -1 and 1, and range from 0 to pi. Y can't be pi over 2. Remember, because that is the vertical asymptote. So if you look at those 2 points, for example, we have the pairs. So let's look at this one has coordinates 0, 1. This one has coordinates pi minus 1. So 0, 1 goes to 1, 0. I minus 1 goes to negative 1 pi. Vertical asymptote x equals pi over 2 will become horizontal asymptote y equals pi over 2. So those are the transitions. Interchange x and y for the inverse. VA becomes HA. And the graph looks like that. So this orange part, if you will, remains. And now this is the inverse, symmetric with respect to the line y equals x. And this has a little bit more detailed as far as the graph is concerned. And you can see those pairs, by the way. This is clearly 1, 0, and this is clearly negative 1. Fine, let's just write that. So this is 1, 0, negative 1 pi. Find secant inverse of 2. We let theta represent that. Then by definition, secant theta becomes 2. We may not remember the secant, but we know it's the reciprocal of cosine. So if secant is 1 over cosine equals 2, cosine must be 1/2. The reason we go to cosine because everybody remembers this is a common arc and theta is pi over 3. Inverse cosecant function. Y equals cosecant is 1 over sine. So we graph a sine function, we go indefinitely on both sides. So look at one complete cycle, this one, and flip it over. And we write y equals cosecant x, domain is all real numbers except x can't be n pi because if you set the denominator equal to 0, sine is 0 at x equals n pi. Okay, so that means x equals n pi would be the equation of vertical asymptotes. Range the same as secant all real numbers except negative 1 to 1. And this is not a 1-to-1 function. It fails a horizontal line test, doesn't have an inverse. What do we do? Restriction. How do we restrict it? Sine we restricted from negative power to power 2. We do the same thing here from negative power to power 2, these two pieces. And they cover everything we want. In other words, y equals cosecant x, we restrict the domain from minus power to power 2, and x instead of can't be n pi, there's only it can't be 0. We haven't lost the range, the same thing, but now this is not a 1-to-1 function. This one with the restriction is a 1-to-1 function. Because it's a 1-to-1 function, it has an inverse. So y equals cosecant inverse x means x equals cosecant y. The domain, range becomes the domain. All real numbers except numbers between negative 1 and 1. Range, domain here becomes range from minus power 2 to pi over 2. So pretty straightforward, everyone. In short, another one-to-one. Restriction makes it one-to-one, gives rise to its inverse. So let's look at those 2 points. This has coordinates power to 1. This has coordinates negative power to 1. And the vertical asymptote is the y-axis. The y-axis has the equation x equals 0. So this becomes 1 comma power 2. This becomes negative 1 negative power 2. VA becomes HA, y equals 0. Okay. So we see the transition, I hope. Here's the graph. 1 power 2, negative 1 power 2, horizontal asymptote y equal to 0. And on the same set of axes, they look like that, symmetric with respect to the line y equals x. So the red one is that piece, and the blue one is that piece. As an example, let's find cosecant inverse of 2. Let it be theta. By definition of an inverse, cosecant theta must be 2. We don't know cosecant, but we do know sine, and we do know that cosecant is 1 over sine. So if cosecant is 2, sine is its reciprocal 1/2. Therefore, theta must be pi over 6. Inverse cotangent function. Cotangent is cosine over sine, and the graph looks almost like y equals minus x cubed, just to remind you how it looks like, of course, from 0 to pi, and then it goes indefinitely on both sides. Y equals cotangent x. Domain is all real numbers, except x can't be n pi, because whatever makes the denominator 0 is excluded, and that gives rise to vertical asymptote x equals n pi. Range is all real numbers, not a one-to-one function, fails. The horizontal line test does not have an inverse. We restricted to only one of those from 0 to pi. So same function, we just restrict the domain from 0 to pi. You don't have to write that anymore. We know that x equals 0 and x equals pi are VA, because we didn't have the equality. We don't have to exclude anything. Range doesn't change, and that's the key. You can't lose the range. Now you're dealing with a one-to-one function. and therefore it has an inverse. So y equals cotangent inverse, means x equals cotangent y, range becomes the domain from negative to positive infinity, domain becomes the range. And as I mentioned, the restriction as mentioned. And so it's very straightforward. This point has coordinates power to 0. So this goes to 0, power 2, just as an example. VA, x equals 0, x equals pi. They become HA. Okay. Y equals U, Y equals, and it looks like that. Let me erase mine so you can see this. Okay, so that's the graph of the cotangent inverse. And so find cotangent inverse of 1. Let theta be cotangent inverse 1. That means cotangent theta equals 1. It's a common arc. You know the answer, power 4, and you're done. Approximation using a calculator, 2 decimals. By the way, I think when there are common arcs, you know the answer. It's very easy to get that. I want to show you how the calculator works in case you come across something which is a little bit more complicated. So secant inverse 3. Remember, the calculator has the key for the inverse trig functions, sine, cosine, tangent, not the rest of them. So we know secant is 1 over cosine. Therefore, this is the same as cosine inverse of 1/3. You put that into a calculator because it's not a common arc, and you want 2 decimals next to 3 zeros, so it's 1.23. And by the way, pay attention that both of them have the same restriction, 0 to pi. You don't have to worry about anything. Cosecant inverse of -4. We don't have cosecant inverse key. We put it sine inverse, and we're going to write the reciprocal of this number, -1/4. We put that into a calculator, gives us the answer, and we want 2 decimals. 5 doesn't change. -0.25. Cotangent inverse of 1/2. Now, because it's positive and it happens in the first quadrant, you can go with the tan inverse of 2 for the sake of argument. But if it's negative, it can't happen because tan goes from negative power 2 to power 2 and cotangent goes from 0 to pi. That's why when they want to find the inverse, they go to cosine inverse. But how do they move from cotangent to cosine? We know cotangent is x over y. And so if x is 1, y is 2x squared plus y squared makes it 5. 1 squared plus 2 squared. And cosine is x over r. So first and foremost, this one is 1 squared plus 2 squared equals 5. And cosine theta is x over r. So cosine inverse of 1 over square root of 5. That's important to know. And so you put that into a calculator, and we said, see, cosine inverse of 1 over 5 to the power of 0.5. I hope you see that this means square root of 5. We want 2 decimals. 0 changes to 1 and becomes 1.11. Now, so the answer is 1.11. Given cotangent inverse of x, pay attention to this one. If x is positive, you may use tan inverse of 1 over x. In other words, if this number 1/2, it's positive, just use the tan inverse. And that gives you exactly, so tan inverse of 2, because the reciprocal of 1/2 is 2, everybody. And that gives you the same answer. But what happens here is interesting. This is x over y, so negative 2 over 1, because in the second, remember, cotangent goes from 0 to pi. Cotangent and cosine 0 to pi. So if this is negative 2, this is negative 2 over 1. X is negative, y is positive, r happen to become the same, square and add them up becomes 5. So again, x squared plus y squared equals r squared, everybody. So I hope it's clear to everybody that y, again, we get 5 just like the previous one. Okay. Let's just quickly show you that one again. So we have x squared plus y squared, again is 5. So r is square root of 5. So cosine is x over r, negative 2 over square root of 5. Put that into a calculator. With 2 decimals, we are interested in this one, and it's going to go up because next to it is 7, so 2.68. On the other hand, take a look at what I'm going to tell you. This is extremely important. Given cotangent inverse of x, if x is less than 0, see, when it's x is larger than 0, go with tan inverse of 1 over x. But if it's less than 0, you may use tan inverse, and then you have to add pi. Why is that? Tan is negative in quadrant 4. Remember, tangent, just like sine, goes from negative power 2 to power 2. So because it's negative, the reciprocal is negative. It gives you an answer in the 4th quadrant, but you want it in the 2nd quadrant. So how do you go from 4th to 2nd? You have to add pi, since tan is negative in quadrant 4 and cotangent t is negative in quadrant 2. That's why. So take a look. Tan inverse of negative 1/2 is an answer. You add pi and you get exactly the same answer as this one. And as I mentioned, the answer is 2.68 because we are going to go with 2 decimals. Let me. So just be careful when it comes to cotangent. So it's not just a reciprocal of tangent unless it's positive when it comes to finding the answer. Write the trigonometric expression as an algebraic expression, sine of tan inverse of u. So tan inverse of u is an angle or arc or theta. By definition, tan of theta is u, and we want sine of theta. So tan of theta is u, find sine of theta. That's the question. If you want to go with the identities, we can go with one of Pythagorean identities. 1 plus cotangent squared is cosecant squared. And cotangent is 1 over tangent. So we can replace it with 1 over tangent. Cosecant is 1 over sine. So we change it to 1 over sine squared. The left-hand side, I can take the LCD and becomes tan squared plus 1 over tan squared. So take a common denominator. So 1 over sine squared is the left-hand side. If you write the reciprocal of the left-hand side becomes sine squared. So in other words, flip this one over, you get sine squared. And so let's plug in. Tangent is u. So u squared over 1 plus u squared. So what is sine theta? Well, take a square root plus minus. However, sine and tan, both of them happen in the fourth and first quadrant from minus power 2 to power 2, and they have the same sign. In the first quadrant, both of them are positive. In the fourth quadrant, both of them are negative, so you don't need a plus minus. Sine and tangent have the same sign. In other words, if sine is positive, so is tangent. If sine is negative, so is tangent, and vice versa. So that's extremely important. Understanding the quadrant is truly important, class. We're going to repeat that with a slightly different method. And again, so it's the same question. Tan inverse of u is theta, and again, all of this that was discussed before, u is tan theta, u is between negative and positive infinity, theta is between negative power 2 and power 2, quadrant 1 and quadrant 4. In quadrant 4, both of them negative. In quadrant 1, both of them positive. I mean sine and cosine. So you're looking for sine of theta. So here's an interesting methodology, somewhat different. Let's multiply by cosine theta over cosine theta, which is equal to 1. So if I put this one underneath this one, sine theta over cosine theta is tan theta times cosine theta. And cosine theta is 1 over secant theta. So it's tan theta over secant theta. Again, just some manipulation. And as you know, 1 plus tan squared is secant squared. And so this is tan theta. This is the square root of that. And in quadrant 1 and quadrant 4, secant, just like cosine, is positive, remember? So tan theta over the square root of 1 plus tan squared theta. Replace the tan theta with u, and you get the same answer. Again, this is maybe a tad more complicated than the previous page, but that's just a method in case anybody is interested. So there are different methods of tackling this class. And there are more methods. All right, let's look at more examples. In this case, the very first example, tan of sine inverse of u. Remember, we did sine of tan inverse of u. So that is an angle, an arc theta. So let it be the case, which means sine theta is u, we want tan of theta. That's the meaning. And sine and tan, we have established, they take place in the first and fourth quadrant. They have the same sign. Remember the restriction that we put for the inverse. So tan is sine over cosine. This is actually easier. Sine, we have it. Cosine is square root of 1 minus sine squared, and it's positive. By the way, I'm assuming, everyone, when we know sine squared theta plus cosine squared theta equals 1, then, for example, we can see the transition. Sine squared is 1 minus cosine squared is 1 minus sine squared, and each one is plus minus the square root, okay? But the reason we don't have a plus minus, because we know it's positive. So we are going to replace the sine theta with u, and reminding everyone, quadrant 1 and quadrant 4, that's where sine inverse and tan happen. So sine and tan have the same sign, and cosine, by the way, is positive in the first quadrant as well as the fourth quadrant. Tan of secant inverse u, so we are going to work on this. We call this theta. That means u is secant theta. Reminding you, all of this, we've discussed that for the restriction that we put on secant inverse. And the question is, what is tan theta? Okay. We have a simple Pythagorean identity, 1 plus tan squared equals secant squared. So tan squared is secant squared minus 1. So that means tan is plus minus the square root of the right side. And secant is u. So tan squared is u squared minus 1. And tan is plus minus the square root of u squared minus 1. The question is it positive or is it negative? Well, in the first quadrant, tangent is positive. In the second quadrant, tangent is negative. Secant, just like cosine, goes from 0 to pi, first quadrant and second quadrant. So you have to have both signs because you don't know which quadrant. But you do know that secant is the inverse. The restriction is 0 to pi, therefore can be positive or negative. So I want to distinguish between them to see why, for example, this you know for sure is positive, this one can be both, and why. Cosine of sine inverse of u. Sine inverse of u actually means the same thing, is theta, and theta is between negative power 2 and pi over 2. And now we want to rewrite the meaning. Sine of theta is u, find cosine theta. Sine of theta is u, find cosine theta. First and foremost, first and fourth quadrant, that's the restriction on sine. In the first and fourth quadrant, cosine is positive. Sine squared plus cosine squared is 1. Cosine is square root of, again, we are using that. Cosine squared is 1 minus sine squared, and cosine squared is square root of 1 minus u squared. Let's actually do this. So I want to make sure that we understand what's going on here. So u squared, okay? So cosine squared is 1 minus u squared. Cosine theta is plus minus that. However, in the first and fourth quadrant, cosine is positive, nothing to worry about.